Hi there, Mr. Boyle's Physics, and another installment of Properties of Matter with Nova as well. Today we're going to be talking about the gas laws and particularly about pressure and volume, and then pressure and temperature. But let's first of all talk about pressure and volume. Now, I've got a bicycle pump. I left my bike in my classroom before Christmas. I'm not going to get that bike back until at least mid-February. So that's a little bit of a sore point in my heart, but that's fine. We'll move past it. Now, why have I got a bicycle pump? Well, we know that when you pump up a tyre, you're building up pressure. Now, with this thing here, when I go up, alright, there is a big volume here. There's a massive volume here. So when I press down, I will be decreasing that volume, okay, because I'm pushing the air out. Now, the air is coming through here. I've not done anything with that. So there's not really much pressure going on here. Okay, there's a bit of pressure as it pushes down, but the volume's changing, alright, because the air is moving. Now, what would happen if I put my fingers on the end of this pump? Okay, so if I was to do this now, and I was to press down, I'm increasing pressure, and if I can keep hold of this quite firmly, I'm not able to get past this point here. So I've decreased the volume is now decreased because I've increased the pressure. The volume is now decreased, and if I was to release the valve, I can go down again. Alright? So, what do I mean by this? Well, basically, when you increase pressure, then, and the volume is a set volume, like this tube here, you will decrease the volume of the air inside this. Okay, so when I push down and I've got this closed, you can compress the air, but the volume can get smaller. So high pressure means low volume. Okay? However, if I have very low pressure, that means I should have lots more volume. So when I lift this up here, I've got loads of volume now, okay, and I've hardly got any pressure. So can you see that low pressure means high volume, but high pressure means low volume, okay? So that is pressure volume law, and I'm going to talk to you about that in the PowerPoint. So hopefully that makes a little bit of sense once I've talked about it on there. Okay, let's skip to the ironing board. Let's go. Alright, moving on from pressure and volume, we're going to talk about pressure and temperature. Now, I'm just ironing my shirt from yesterday's video. If you've not checked it out, check it out now. Now, this here is an iron, as some of you will know, and it has a set volume, doesn't it? Now, if I was to plug this in, which I have, the temperature is going to start building up. A bigger temperature means that you're going to have bigger pressure. Okay, why? Because the particles are moving around and are hitting. The more, when they're got higher temperature, they're more excited, so they move faster. So then they hit the walls faster, and so therefore there's more force, which means there's more pressure. Now that pressure is building up. So high temperature means high pressure. And when I would do this, I release that pressure. Okay? So when we have a high temperature, we have high pressure, and I can release the pressure that's been built up in this iron. Alright, so that's just a wee intro to this video. Hope those things make sense. If not, then I'm going to explain it much more in detail through the PowerPoint. Now, scooch, I'm going to do some ironing. Hi Mr. Boyle's Physics family. I hope you enjoyed those analogies, and it's time to move on to another lesson on properties of matter, our new topic that we've been looking at. You know, like, share and subscribe, the constant message in an unprecedented time, alright? But let's move on. Properties of matter. We're talking today about gas laws, okay? So gas laws. Moving on to the next thing. Now, our learning intention today is to learn the equations that apply when the temperature, pressure, and volume of gases are changing. And the success criteria is the kinetic theory will be successfully used to explain each of the three gas laws. Now, remember, everything from now on is in Kelvin. Everything from now on is in the Kelvin scale, not the degrees Celsius scale. Because remember, Kelvin scale is the Celsius temperature plus 273. You must always convert. It will not work. None of these equations will work if you use degrees Celsius. You must change this into the Kelvin scale. So please remember that you have been warned. Now, let's first of all look at the pressure volume law, or Boyle's law. Now, the pressure volume law is a law that basically talks about the fact that gas particles collide with the walls of a container, okay, as we can see in the diagram, and they will apply a force to those walls. Now, the sum of all those forces divided by the surface area of the container defines the pressure of the gas, okay? So just like we had P equals F over A being the pressure of the gas particles on the outside of the container. Okay, now what would happen if we took that plunger and pushed it further in? Okay, well, what would happen is the volume would decrease, the particles then would collide more with the walls more frequently. So, for example, if I had a massive amount of ping pong balls thrown in this lounge that I'm sitting in right now, they would hit the walls and it would work. But if I took all those, say I took 1,000,000 of those ping pong balls and then put them into a cupboard, they would hit the walls much quicker. Okay, or not much quicker, more frequently. They're not moving faster, they're moving more frequently and hitting the walls more frequently. And as they do that, the average force then increases, and therefore pressure under F over A means that the pressure also increases. Okay, so volume decreases, particles collide more frequently, average force increases, so therefore pressure increases because force divided by area equals pressure. Okay, now we would normally do an experiment with this, but we can. This is what it would look like. All right, and in this experiment, we would push an air pump down. Okay, obviously increasing pressure, kind of similar to what I did in my experiment just earlier. And we would see that the compressed air on the left-hand side here would get smaller. So increase pressure, decrease volume. When we increase the air pump, i.e. decrease pressure, the compressed air would become greater. So therefore you'd be increasing volume. So decreasing pressure increases volume. Increasing pressure decreases volume. Okay? And that's a simple experiment that you could be asked about in a National 5 exam of some sort. Okay? Now, this is the important bit. Pressure, volume, or Boyle's law. What does it look like in terms of graphs? And you could get asked about graphs in both the written section and in the multiple choice. So, when you increase volume, you decrease pressure. When you increase pressure, you decrease volume. And that's what the first graph looks like. It's a nice wee curve. Now, if we want it to be a straight line, which physics, we love to do that, we're going to have to make it inversely proportional. Okay, so we're going to have to make, instead of V, we're going to have 1 over V. Okay, 1 over V. And then we're going to get, then that will plot a straight line for us. Okay, so that's, make sure you look at the axes, because in multiple choices, they will give you a graphs, and if you don't look at the axes, they will catch you out. So please make sure you do that. Now, excuse the fact that the format of Google Drive is not actually allowing me to show you this properly, but P1V1 equals P2V2. Okay, that is the important equation. In equations, you will get something before, like a pressure and volume before, and then you'll get something like a pressure or a volume afterwards, and then you will have to find the missing component. Okay, so you'll be given 3 pieces of information with 1 missing, and you have to then use P1V1 equals P2V2 to find that out. If it's only pressures and volumes. Remember, pressure in pascals, volume in meters cubed. Now, what's the kinetic theory? Well, the kinetic theory is this. As the volume decreases, the particles will collide more frequently with the walls of the container, and therefore the average force on the walls increases, and therefore means that pressure increases. That there is the 3-mark golden answer for kinetic theory for pressure and volume. So make sure you know that, please. Right, let's move on to pressure, temperature, or the Gay-Lussac's law. Okay, so in this one, we have another syringe, okay, and we've got a kind of small temperature, okay, now of 20 degrees. The kinetic energy of a gas particle is directly proportional to its temperature. So for example, if you give a particle more higher temperature, then it's going to move faster. Okay, its kinetic energy is going to be greater. Okay, things that are warmer are going to move faster. Okay, now what happens when we increase that to 50 degrees? Well, when you increase it to 50 degrees, the particles start to speed up. And if they speed up, that means they're going to hit the walls more frequently. And you can kind of see where this is going, with that, which means that they'll be hitting it with greater force, which therefore means that pressure increases. So it's all about the fact that the particles get sped up,
They hit the walls more frequently. Greater force, so therefore pressure increases. Okay, so when you increase the temperature, you're actually increasing pressure. Okay? Now, think about this with a deodorant can. If you were to put a deodorant can in a fire, the volume stays the same, but the pressure is going to be building because the temperature is rising, the particles are getting excited, they're hitting the walls more, and before you know it, it explodes because it explodes because it can't contain it anymore. So this is something kind of similar. Again, it's more tricky to do this, but the idea is when you increase temperature, you should have an increase in pressure from your sensor. Very simple, very straightforward. Whatever you get given in an exam or anything like that that's involved with this, it should be fairly self-explanatory. Now, what does this look like? Well, this is the key thing here. If you were to have the temperature scale in Celsius, you would get a very odd-looking graph. Okay? If you have it in Kelvin, you get a very nice-looking graph. That's why I keep saying put it in Kelvin. And if you do it in Kelvin, all right, that's meant to say a K down there, you get a straight line through the origin, because at 0 Kelvin you should have zero pressure because there's no particles moving at 0 Kelvin. However, at 0 degrees Celsius, you know that that's 273 Kelvin. So therefore there will be pressure. So if you were to move the graph here into the negative axis, you would eventually get back to minus 273 degrees Celsius, which is 0 Kelvin, which would be where his pressure is 0. Okay? Now, and again, excuse the format here. This one is pressure P1 over P2, or T2, sorry. That's meant to be the line there moving across. P1 over T1 equals P2 over T2. Excuse the fact that there is a weird movement of the lines and that there's two equal signs. That is not in the original PowerPoint. It's just come out very strangely. So P1 over T1 equals P2 over T2. Please remember that. Okay? And again, 3 things will be asked and you'll need to find out the other one. And you need to make sure your answer is in Kelvin, please. Kinetic theory of this: as the temperature increases, the gas particles speed up. The particles strike the container walls more frequently with greater force, and therefore pressure increases. Okay? So, that's us. 2 equations. P1 V1 equals P2 V2. The second one, P1 over T1 equals P2 over T2. Please remember those equations. Okay? And also, just as important, the kinetic theory of those equations. Okay? Hope that makes sense. National 5. Any questions, ask your teacher, and the questions will be on this stuff. Both of these equations. Alright? Very well done.
Well guys, the time it took you to watch this video, it took me to iron this shirt. It takes me ages to iron things. I hope to wear this soon as we reunite in school. Some point, hopefully, in February. Until next time, Mr. Bill's Physics.